So okay, in this video we're going to calculate the expected value of the standard normal distribution and the variance of the standard normal distribution. Okay, so the expected value firstly. So the expected value of x, so we are given that x is distributed normally 0, 1, which means that its PDF is equal to this. So we have some random variable connecting some abstract probability space with mapping some random probability space onto the real line, and the PDF structure is given by this. And we know that the expected value of such a random variable is given by the integral between negative infinity and infinity of x times little f of x dx. So if we just fill that in, we get that it's equal to the integral between negative infinity and infinity of x over the square root of 2 pi times e to the negative x squared over 2 dx. And this looks an extremely easy integral to compute compared to the integral that we had to deal with last time. This is absolutely pips. We'll pull out that 1 over the square root of 2 pi. The integral between negative infinity and infinity of x e to the negative x squared over 2 dx. Now, we showed in the previous video that if you take e to the negative x squared, we'll just go over this again, if you differentiate that, you get negative e to the negative x squared over 2 times x. So I'll put the x down the front. So basically, when you integrate the exponential, it just remains the exponential, and then you integrate the inner thing, which will give you negative x. So we've got the negative x out the front. So the antiderivative of x e to the x, so antiderivative of x e to the negative x squared over 2, and I think it's a pity we don't have some sort of notation for antiderivative to separate it from integral. I suppose indefinite integral is often used to mean antiderivative, but in a way the concept of integration is very different from the concept of differentiation. Yes, in the real line they are totally connected by the fundamental first and second fundamental theorem of calculus, but in more abstract metric and measure spaces they are not connected at all. So antiderivative of x e to the negative x, so I think it would be useful to have some, maybe there probably is, but the antiderivative of x e to the negative x squared is going to therefore equal negative e to the negative x squared over 2. Okay, so excellent. So we can then apply the second fundamental theorem of calculus and say that this is 1 over the square root of 2 pi of this antiderivative evaluated at, so we're going to take the limit as n approaches infinity of negative e to the negative n squared over 2, and then again if you put in negative infinity to this, that's going to be, it's completely symmetric, so we're going to get minus e to the negative n squared over 2. So if you think about this as a sequence, well, it's perfectly true that for any n, a finite number, this is going to be equal to 0, because you're going to have a plus 1 here and a negative 1 here. So taking the limit of zeros. And if you want any more convincing, both of these go to 0 anyway as n approaches infinity. So if you split it up into the limit of the sum of the limits, then it would still be 0. So this is going to be equal to 0. So the expected value of our standard normal distribution is indeed equal to 0. Now time for a bit of a more difficult calculation. The variance of x we know is equal to the expected value of x squared minus the expected value of x squared. Okay, so we know that the expected value of x is 0, so we can put 0 into there and get 0 squared. So this just becomes the expected value of x squared. Now we have a formula for the expected value of x squared. By the law of the unconscious statistician, this is equal to the integral between negative infinity and infinity of x squared times little f of x, which in this case is 1 over the square root of 2 pi e to the negative x squared over 2 dx. Now, time for some integration by parts. So if we look at this, 1 over the square root of 2 pi times the integral between negative infinity and infinity. Now split it up into two things. Let's split it up into x times x e to the negative x squared over 2 dx. Now, why do we want to do that? Because we need one thing that we can differentiate and one thing that we can anti-differentiate. I cannot split this up into x squared e to the negative x squared over 2 because I cannot anti-differentiate e to the negative x squared over 2, and if I differentiate it, it's just going to make something worse. Instead, what I'm going to do is I'm going to split it up into x times x e to the negative x squared, and we can anti-differentiate this. So this is the thing we're going to anti-differentiate, and this is the thing we're going to differentiate. Okay, so then just apply the integration by parts formula. If I just get, let's just remind ourselves of the integration by parts formula. So the integration by parts formula is that the integral of f of x g prime of x dx between a and b is equal to f of x, well, it's equal to f of b g of b minus f of a g of a minus the integral between a and b of f prime of x g of x. Okay, so basically I'm letting this equal g prime of x, and I'm letting this be f of x. So on this side we have this thing here. Now, so it's going to be equal to f of b, so that is infinity. Great, so we're going to have to take the limit as n approaches infinity of n, and then we've got g of b. So what is the antiderivative of g? We know that the antiderivative of x e to the negative x squared is equal to negative e to the negative x squared. So we get therefore negative e times negative e to the negative b squared, sorry, no, not b squared, n squared over 2. So we're putting in b here, but b is converging on infinity. Okay, and then what we get is minus f of a, which is minus negative n there, times g of a. So I'm putting in negative infinity. Now f of negative infinity is the limit as n approaches infinity of negative n. So g of a is going to be g of negative infinity, which is going to be the same thing as it. You don't even need to bother there because it's completely symmetric, so we just get this back again. If we take the limit as n approaches infinity, that gives us this term here. Okay, and then what we have is minus the integral between negative infinity, oh dear, that's out of screen, minus the integral from negative infinity to infinity of f prime of x, well that's great because that's just 1, times g of x, which is, g of x is equal to negative e to the negative x squared over 2 dx. Okay, so now let's take a look at this limit. Well, if we look at this limit, so is equal to, so let's just separate it off so that we know where we are. Okay, is equal to the limit as n approaches infinity of, well, we have two things here. We have one is going to be negative, one is going to be negative as negative as well here, because this negative here is going to cancel with this negative here, and then we're just going to get two negatives. So we'll get to negative 2n e to the negative n squared over 2. Now, you might think that's a difficult limit to calculate, but because we've got one thing that is growing infinitely and one thing that is getting infinitely small, but we can just apply L'Hopital's rule here. So we can say that this is the limit as n approaches infinity of negative 2n over e to the n squared over 2. Oh no, that's not going to work because this is now growing on infinity. L'Hopital's rule was for when you have two things going to 0, isn't it? Okay, so that's not going to work. But basically, this exponential is shrinking down to 0. The rate at which it is going to 0 is far greater than the rate at which this is going up. Basically this is actually equal to 0. This beats out this term here. So overall, and the reason is, I'm sure you will be able to do this with L'Hopital's rule in some way, maybe by inverting it, by instead saying the limit as n goes to infinity of 1 over n here and 1 over n here, and then would that work? That probably might work. Yes, that actually does look like a good way to go. Let's say the limit as n approaches 0 of Oh, wait. Yes, we'll do that. Negative 2 over n. Let me get some more paper. Negative 2 over n of e to the negative 1 over n squared to the power of 2. So do those things both go to 0? This is going to go to 0, and as this goes to 0, this is going to blow up. So this overall thing is going to go to 0 as well. So if we we can apply L'Hopital's rule to this now. It's the limit of the derivatives of those things, and if we differentiate this one, we'll get minus 2 e to the negative 1 over n squared over 2 times this thing here, which is negative. Oh, I think I've. No, that's fine. Negative. If we differentiate this thing here, we get the 2 will come down. That will cancel with this. We'll then get minus 1 over n, and then we're going to have to differentiate the thing in here as well now, which will give us 1 over. If we differentiate this thing, we'll get negative 1 over n squared. That doesn't look right. Let me just think about this again. Right, so let's rewrite this out. Negative 2 e to the negative, if we write this out properly, it's negative 1 over 2n squared, isn't it? Which is equal to 2e to the negative a half n to the negative 2 over n, of course. And we want to take the limit of that, so we want to take the derivative of the top and the bottom. So if we take the derivative of the top, we get 2e to the negative half n to the negative 2 times, now, it'll be negative a half, and then we want to differentiate this, so it'll go down to, you'll take times negative 2 times n to the negative 3. So that probably was going to work there. Okay, and then it'll be over now, it'll be over 1. So, okay, we've gone from bad to worse because we're now dividing through by n to the negative 3. But basically, so I don't know how you prove that, but this exponential term does beat out the constant term. Maybe you'd expand it as a Taylor series and show that. Would that work? Can I do that? Not even sure I can do that. No, but it does work. You do. It does approach 0, that limit. So this bit here of this integral goes to 0. Okay, so here is all we're left with. The negatives cancel one another, and you get the integral between negative infinity and infinity of e to the negative x squared over 2 dx. And we know what that is going to be equal to. Where did we? Okay. When I've lost something in the process of this, so we know what that integral is going to be. We know it's the square root of 2 pi, but the variance isn't equal to 2 pi because the variance was 1 over 2 pi times this integral, and I forgot to tag this 1 over 2 pi along with all of this. So 2 pi, the square root of 2 pi divided by the square root of 2 pi is going to give 1. So the variance is overall of a standard normal distribution is overall equal to 1. Okay, so if you believe this rubbish about the limits, I don't know how you prove that. I'm sure if you Google it, you will be able to find some lovely analysis on how to do that. Okay, right, so what is the final thing I want to say? Oh yes, I want to talk about the CDF of the standard normal distribution. So the CDF of the standard normal distribution would be the probability that x is less than or equal to x. So if we have a picture, it would, if you have some x, which is an element of the real numbers, it would be equal to the integral. It would be the integral from negative infinity to x of e to the negative x squared over 2 dx, and I've forgotten the 1 over 2 pi, square root of 2 pi. So it would be 1 over the square root of 2 pi, the integral from negative infinity to x of e to the negative x squared over 2, and that's bad because I've used x twice, so I should replace this by a dummy variable, dt, because it doesn't matter, it's just going, it's a variable that goes when you integrate. Okay, so the intuitive meaning of that is the area under this standard normal distribution curve. But it turns out that this is very, very difficult to calculate, and in fact, the only real successful way that we have of calculating it is approximations. I.e., we can get series which will converge on being equal to it, and we can drum it up to so many terms that it's within 10 decimal place accuracy or whatever you want, and you can basically get a computer to do that, and you have these statistics tables which tell you what this value is, and because it's so important, we define it as a new function, which is phi of x. So phi of x is defined to be equal to this. It's the probability that x is less than or equal to x, or you can view it as the area under the standard normal distribution all the way up to your value x. So that this is the CDF of the standard normal distribution. And to get round the fact that we can't actually get an explicit formula for it, we just call it phi of x, to feel like we do have an explicit formula for it, even though we don't. CDF of standard normal distribution. Okay, so just a quick observation, which is that phi of negative x, so if you take phi of negative x, that's the area up to, say, here. So if this is x, this is negative x over here. The area up to there, well, that's going to be equal to the same as the area, let me get another pen, it's going to be the same as the area from x all the way up to infinity. Basically this is equal to 1 minus phi of x, and the reason, I hope, is obvious, because the area under this whole curve is equal to 1. The area up to negative x is going to be the same as the area from x to infinity, which is 1 minus the area from negative infinity up to x. So that is just a quick symmetry property of the CDF, the standard normal distribution, this phi function, and that actually turns out to be the crux of solving many of the problems that you'll see concerning this distribution.